And we will now talk about the two-factor ANOVA, a situation where we test two variables at the same time and also how they interact with each other. And we will use the example from the book Statistics Explained by Steve McKillop on page 180. And in this example, we look at the growth of cockroaches that are raised in 3 different temperatures and 3 different humidities. We have 3 observations in each square, that is each combination of temperature and humidity. And we have the average for each temperature, and we have the average for each humidity, and also a total average. And the question is, does the growth differ between different temperatures? And does the growth differ between different humidities? And also, does the temperature affect the growth in the same way in all humidities? Let's have a look at how we could analyze this. First of all, we could look at temperatures. And again, here we're only going to look at the degrees of freedom, just to get a feeling for how the test is set up. First of all, we have the total degrees of freedom. We have 9 squares with 3 observations in each square. 3 times 9 is 27, and that gives us 26 degrees of freedom. We have 3 different temperatures. That is 2 degrees of freedom between temperature. And we have the degrees of freedom for within temperature, or the error component, a random variation. And the between component and the within component has to sum up to the total, so we get 24 degrees of freedom here. And this would be a single factor ANOVA for the variable temperature. We could also do exactly the same for humidities. And of course, since the setup is completely symmetrical, we would get the same degrees of freedom here. These analyses are okay to do, but we don't get a complete analysis. First of all, if we would test the effect of temperature, we know that this error component includes a lot of variation from humidity that we don't take into account. And this might make it difficult to achieve significance for the variable temperature alone. And secondly, we don't know if all the combinations of temperature and humidity react in the same way. A last simple thing that we could do is to simply test all the combinations separately. Test the effect of squares. Total degrees of freedom here is still 26. And we have 9 squares, so the between square component degrees of freedom is 8, which gives us an error component of 26 minus 8, which is 18. We can also get to this degrees of freedom by seeing that we have 9 squares and we have 3 observations in each square. That is 2 degrees of freedom per square. 9 times 2 is 18. This means that we have reduced the error term. Now the error term really only includes variation that we cannot explain with our models, our temperature or our humidity. So this is not bad, but we can't tease out the effects of temperature and humidity from this setup. We need a more complete analysis. We have the temperature, we have the humidity, we also have a possible interaction between temperature and humidity. We have the error, and we have the total. Total degrees of freedom is, as always, 26. Between temperature, that is 2. We have already calculated this. Between humidity is also 2. We've calculated that here. The interaction is the trickiest to figure out. So let's first look at the error component. We could also write this as the within square variation or the within combination variation. And combination is a combination of temperature and humidity. And we have actually calculated that as well. It is 18 degrees of freedom. In an ANOVA table, the degrees of freedom always have to sum up to the total, in this case to 26. So by simple subtraction, this gives us that the interaction will have 4 degrees of freedom. And this is also the same as the product of the variables 1 by 1. 2 times 2 is 4. The full ANOVA table will of course also have sum of squares and mean square. And the mean square for between temperature is just the variance calculated over the means of temperature. And that is the same for the mean square between humidity. It's the variance calculated over the means over humidity. And the variance for error, the mean square for error, is the same as the pooled variance for all the squares. So, hypothetically, you would be able to set up this full analysis by hand. And you will probably never have to do this, but it is good to know how the analysis works. Now we will focus on what does the interaction term actually means. A significant interaction means that we have some kind of non-linear relationship between temperature and humidity. When we move from 20 to 30 degrees, something happens. But does the same thing happen in 33 and 66% humidity? Does the effect of temperature change depending on humidity? Or we can also say it the other way around. Does the effect of humidity change depending on temperature? When we do a two-factor ANOVA, it becomes important whether you have fixed or random effects, that is, how you view your variables. This will decide what mean square gets divided by what in order to get the F values. In a Model 1 ANOVA, fixed effects, that is, we are interested in exactly these temperatures and these humidities, and only these. When we do the significant test, we would divide all the mean squares with the error factor. The interaction with the error, and the humidity with the error, and the temperature with the error. If we had a Model 2 ANOVA, random effect, that is, if we view our temperatures and humidities as random samples, we're just interested in if temperature in general has an effect on growth. We would compare the interaction with the error, but we would compare the temperature with the interaction. And this gives, of course, different F values and different degrees of freedoms for the F test. This becomes even more complicated if we have so-called mixed models. That is, if we view one variable as fixed and the other one as random. In the future, when you perform ANOVAs, be sure to check the degrees of freedom to see that they are what you expect them to be. That is, if you're really testing the model you want to test.